which we called a vector space. And when we talk of a space in mathematics, we are talking about a set V and some two operations. So for vector space, the two operations were addition and multiplication, and scalar multiplication. Then we described, or we listed the properties that are satisfied by those two operations to give us our structure known as a vector space. So from the vector space, we looked at a subspace. Then from the subspace, we looked at the basis for a given vector space. We looked at linearity. We looked at how to check that a given set is linearly independent or linearly dependent, and so on. So the first chapter, somebody who is giving us the echo, please, you can mute your microphone. Mute your microphone, then you will unmute in case you want to talk to us. So the first chapter is just a review of linear transformations. We also did some linear transformations in linear algebra 1. So we start from reviewing the concepts we did in linear algebra 1 about linear transformations, and probably we add in a few concepts as we build a foundation for linear algebra 2. So chapter 1 is the review of linear transformations. We will look at 4 sub-chapters or 4 sections. We will define the linear transformations and then look at properties of linear transformations. We will look at the composition of linear transformations. We will look at what we call the kernel and the range of a linear transformation. Then we look at the inverses together with examples, and that will mark the end of chapter 1. And my plan is that in this first lecture, we should be able to end chapter 1. Okay, so we proceed. What is a linear transformation? If we let T be a map that takes vector space V to vector space W, so it is a mapping. So we let T be a function from vector space V to vector space W. Then this T is said to be a linear transformation from V to W if and only if for all vectors U and V and for all scalars C, there are 2 properties that this map should satisfy for us to call it a linear transformation. So the properties are A and B. It should satisfy, this is the linearity actually. This transformation should be linear under addition. What do we mean by linearity under addition? That when we apply it on a sum of 2 vectors U and V in V, that one should give us, should be the same as applying it on individual terms. Then the part B, it should satisfy the scalar multiplication. Applying it on the scalar multiplication is the same as the scalar times applying it on U. So any mapping that satisfies these 2 properties, A and B, is said to be a linear transformation. And in a special case, when V is equal to W, if that map is mapping within the same vector space, then we call it a linear operator on V. So linear operator transforms things and brings them back into the same set. Now, in Calculus 1, we looked at functions, or what we call mappings. So functions work as a machine. You give it an input, it processes it, and it returns the output. So likewise, this transformation T, when you give it vectors in V, it works on them according to the way it is defined. and then it returns vectors in W. And so this is a map. So if that map satisfies these two properties, then it is called a linear transformation. And if it is working within the same vector, then we have what we call a linear operator. Okay, so next we look at examples. We want to look at some examples of maps that are linear transformations. So the first example, we are looking at A being an n by m matrix, and we want to define TA to be Rm to Rn. So this is a vector space. In linear algebra 1, we proved that R is a vector space. So Rm is a vector space, is an m-dimensional vector space, and then Rn is an n-dimensional vector space. And we want to define this transformation. It works on a matrix A, and it maps, it picks vectors in the column, and it maps them to the row, and is defined by Tx. When you give it any vector x in Rm, then it computes Ax. Then TA is a linear transformation. So how do we know it is a linear transformation? We need to check the other two properties, A and B. So we let x, y be vectors in this first set. Remember, this first set, we call it the domain. And then this one is called the codomain. So we pick two vectors in the domain, and then we let C be a scalar. Then we want to check the other two properties. The first property is that when we add those two vectors and apply our TA, then this one, from the definition of TA, we use this definition of TA, it is AX. So it will be A then times X. But this is the same as AX plus AY, because A is a matrix and these are scalars, and from the properties, matrix multiplication is distributive over the scalar. And when we look at AX, we know that is TAX. When we look at AY, that is TAY. So you see, property 1 is satisfied. Next, we check for property 2. Property 2 is the TACX for a scalar. This is equal to CX equaling to, yeah, so it is equal to that, and so property 2 is satisfied, and then we conclude that TA is a linear transformation. So if we are given any map, then for us to know if it is a linear transformation or not, we need to check those two properties. Any questions so far? Any
It is
questions?
okay, sir.
Yes, please. I'm hearing. Any question? Can I proceed?
Yes, you can proceed.
Okay, so if there is no question, I can proceed to the next example. Now, before I proceed to the next example, this transformation here, the above example highlights the fact that the matrix M by N, this should have been N by M, sorry, because this matrix A is an N by M, so this one should have been N by M. So the matrix N by M defines a linear transformation from Rn to Rs. So that means that whenever we have a matrix, then it defines a linear transformation. We can transform the M's are the columns and the N's are the rows. Okay, example 2. Example 2, we have T. This T maps R to R2. So this is a linear transformation because the first one is a one-dimensional vector space. The second one is a two-dimensional vector space. So you give it a vector in one dimension, it works on it, it returns a vector in two dimension, which is R2. Defined by Tx is x, then 3x for all vectors x in R. Then T is a linear transformation. So we are claiming that it's a linear transformation. Now next, we can prove the other properties. The first property is A. Of course, we let x and y be vectors in R. Then the T of x plus y is going to be the T of x plus y according to this definition. When we give it a vector x, it returns x, and then it multiplies x by 3. So Tx plus y is x plus y, then 3 into x plus y. I'm using this definition here. So this is going to be Tx, then x 3x. I can put a comma here, it group x 3x, then plus this is y, and then 3y. And you can see that Tx 3x resembles the Tx here. That means y 3y, it is also the T, so property A is satisfied. Next, we check for property B. Property B is Tx is equal to Cx, then 3. So because the C is our scalar that we are multiplying, so now we apply the definition here. This will give us C into x, then 3x, because we can factor out the C, but we know this is x, so it means all properties are satisfied. So that is example 2. Example 3 of a linear transformation. We are defining a vector space.
Excuse me, sir.
Yes, please.
On the example 2, so you mean x comma 3, the way they have defined this Tx, the transformation T x. So you mean this value, it's a value of both x and y, or because when you are putting in here, you're trying to define T into x plus y.
Yeah, because,
and you're saying it
okay. Let me try to explain. To the x and y are vectors in the domain, which is R, one dimension. So when I add them, the definition tells me that I get the first vector, then I multiply by 3 because the resultant should be in R2. So that's where I get this. I don't know whether that answers the question.
Okay.
Okay, so
yes, it is okay.
Example 2, we want to define a new vector space x, capital X, which is a space of all continuous real valued functions defined on a closed and bounded interval AP. So we want to define this transformation. We want to define I to map. The I is mapping X. When you give us X, it gives a real number defined by because it is a space, elements in X are functions which are continuous and bounded. They are continuous, closed, and bounded in this interval here. So when you give it a function, this transformation I, it computes the integral from A up to B of fx t. Then we are claiming that I is a linear transformation. Now we know that the definite integral from A up to B gives a real number. So we give it a function, it computes the integral from A up to B, and it returns a real number. So we want to show that this space is a linear transformation. So here we go. We observe. We need to make an observation that if f is x, then f is closed, then f is bounded. Hence, the integral is well defined. We looked in Calculus 2, where we looked at integration and its application. One of the conditions for a function to be integrable is that it should be continuous and bounded in a given interval. Since the function f is bounded, then we are sure its integral. We are sure this integral. Okay. Obusobozi is making noise in the background. Obusobozi, you can mute your microphone.
I'm sorry.
You unmute in case you want to talk. Okay. So I was still here. I was telling us that if we pick a function here, then that function is this integral is well defined. So in order for us to check the other two properties, we pick two elements of x, but elements of x are functions. So we let f and g be two functions, and then c be a scalar. So to check property A, we need to work out I of f plus g. Now from the definition of if is the integral from a up to b, so that will be integral from a up to b of f plus g, then t dt. I'm using this definition of I. So when we do that, then that is the integral from, we know that this is f of t plus g of t in brackets. We continue to get the integral. We continue to get the integral f of t dt plus this, and we see clearly that this is because this first one here is the if from this. That means this one will also be ig. So property 1 is satisfied. Property 1 is satisfied. And next we check property 2, but I don't have property 2 on my slide, but you can be able to follow it from the notes. Yes, please.
About that property 1,
yes. Hello. I'm hearing. I'm listening. Who is asking? Somebody is asking, and
was it James?
James.
Yes, sir.
Yes. What is your question?
My question is, how did you get in X?
How did I get? How did I get?
How did you get G?
G. Okay, now.
Because here you say
we have F here, but I have the G also. Okay, can anybody answer James's question? Anybody who wants to answer that question? Anyone who can answer James's question? Where do we get the G? Okay. Now, James, if I can take you back, if I can surely take you back, if I can take you back here. Okay, let me take you back to the definition of a linear transformation. We said if TVW is a linear transformation, then T is a linear transformation if for two vectors U and V. So if we are proving property A, we need to pick two vectors from the domain. We need to pick two vectors from the domain and add them and show that this rule holds.
Okay.
Then we multiply them by a scalar to show that that one holds. Now going back to this, for me to prove that this is a linear transformation, I need to pick two vectors from X. I need to pick two vectors from X,
Okay.
and I show that they give me this by I. So the two, what are elements in X? Elements in X are functions. So that's why I pick two functions, F and G. And then I get that. Does that answer your question?
Okay.
Okay. So I was saying that
Yes.
conclude this proof, we need to work out part B. And part B couldn't fit on my slide, but you can follow part B from you can follow part B from from the lecture notes, because I just picked the slides from the lecture notes. Okay. Okay, I think, yeah, so that's it. And next, we want to look at properties of linear transformations. But before the properties, there's an exercise. There are some functions which are given, and you're supposed to prove that they are linear transformations. Now, next time, I want you to go and work out that exercise at an individual level. And the next time we meet, I will allow, I'll pick randomly 3 people, and then I allow you to discuss. I can allow you to share your screen. So what you do, just work out the examples, then take pictures like we've been doing and save it on your gadget. If it save it on a computer or on a phone, then when I ask you to share the screen, you can share the screen and then tell us what you did. So I'll pick randomly 3 people and then you present on that exercise. So our next subsection is we want to look at the properties of linear transformation. So where I write LTs, then those are linear transformations. So the first property is that if we get a linear transformation T mapping V to W, then for any vectors V1 and V2 in V, if we pick 2 elements in V and any scalar C1, and then we get this. When we add here, we should get this at once. In fact, this property, some books give this as a definition of a linear transformation. You see, we said a linear transformation V to W. Okay, transformation T mapping V to W is said to be linear if it satisfies A and B. So this property here is a combination of conditions A and B. In fact, if you want to prove that a given mapping T is a linear transformation, or a given transformation is linear, you simply need to work on this property. If you can prove this property successfully, then you have combined property 1 and property 2. This is for 2 vectors, and it also works in general. More generally, if you have vectors V1, V2 up to Vn, and then scalars up to Cn, then when you add them, the linearity should hold. So this is the first property. Next, we'll continue to look at properties. The other 3 properties are stated in form of a theorem, and that theorem says that if T is a transformation from, if T, a transformation mapping V to W is linear, then that linear maps a zero vector in W. I mean, when you give it a zero vector from V, it returns a zero vector in W because it is linear. When you give it a negative vector in W, then it returns negative. Okay, so this one tells us that